You already know unit testing, regression testing, and integration testing. None of that tells you where the test cases come from. There are two disciplined ways to invent them. One reads only the specification, the other reads only the code. And here is the uncomfortable part. A suite that touches every pass in your program can pass while the program is wrong. The most natural source of test cases is intuition about the problem. Read the docstring and ask which values are interesting. For a function of x and y, 3 and 4 gives you the case x less than y. 4 and 3 flips it to y less than x. 0 and 0 makes them equal and pins the low end. 1000 and 1000 makes them equal at an extreme. 4 pairs, and between them you have covered less than, greater than equality, and the extremes. Mathematical functions make this easy because they come with natural boundaries. Plenty of functions do not. When there is no boundary to reach for, you fall back on random testing, and the trade-off there is blunt. The more cases you throw at the function, the better your odds of tripping over a bug. Beyond intuition, there are two real techniques for manufacturing test cases: black box testing and glass box testing. In black box testing, you treat the function's body as a black box. You do not look at what the code is doing. The only thing guiding your test cases is the specification, the docstring. So you had better hope whoever wrote the function wrote a good one, because that is all you get. For a square root function, you ask a single question: which values of x and epsilon satisfy the constraints the docstring states? You will not test values that violate them, because the author never promised the function works for those. Here is what makes that discipline pay. Because the cases come only from the specification, they are implementation independent. Suppose the author builds square root by successive approximation, and later tests it out and rebuilds it with bisection. My cases do not know and do not care. The docstring did not change, so every case still applies, and every case still checks the same promise. The test suite survives a rewrite of the black box. The list for square root writes itself. For x, start with 0, then a perfect square, say 4, then a value less than 1, like 1/4, then a value whose square root is irrational, like 2. You can never write that answer exactly. Then a handful of extremes at both ends. For epsilon, the same shape. A few reasonable values and a few extremes, then mix and match. 0 paired with an extreme epsilon, a perfect square paired with an extreme epsilon, and onward. That is nowhere near all of them. It is a good start. Glass box testing turns that around. Now the code itself is what guides the cases, and the goal has a name: pass complete. A pass complete suite runs every single pass through the program. So you read the code and let its shape dictate the list. A branch with 3 arms needs 3 cases. One that lands in the if, one that lands in the else if, one that lands in the else. You are no longer testing a promise. You are covering a structure. Loops get the same treatment with 3 cases each. Take a for loop. One case where the body never runs at all, one where it runs exactly once, one where it runs many times. A while loop is identical. A case that never enters, a case whose condition holds once, a case whose condition holds many times. Now count. Every conditional multiplies against every loop, and the glass box testing hands you far more cases than intuition ever did. Pass completeness has a hole in it, and the cleanest way to see it is a function that is supposed to return the absolute value of x. It reads, if x is less than -1, return -x, else return x. 2 cases make that suite pass complete. Test 2. 2 is not less than -1, so we fall to the else and return 2. Correct. Test -2. -2 is less than -1, so we take the if and return the negative of -2, which is 2. Also correct. Every pass has been walked, every case passes, and at this point you would sign off on this function. Now feed it -1. -1 is not less than -1. The comparison is strict, so we fall through to the else and return x unchanged. which is -1. The absolute value of -1 is 1. The function returned a negative number for an absolute value, and the path complete suite never noticed because -1 takes the very same path that 2 took. The bug does not live on a path. It lives on the edge of a comparison. The boundary belongs at 0, not at -1. So glass box testing needs a second habit alongside path coverage. For every conditional, test the value sitting exactly on the boundary and the values on either side of it. Eventually, a case comes back wrong. You ran the suite and the one output does not match what you expected. That is the moment debugging starts, and it is a different kind of work. Black box and glass box gave you recipes. Read the spec, read the code, enumerate. Debugging has no recipe. It takes creativity, and it takes having seen bugs before, which is the unglamorous reason that experience writing code matters so much here. There is no substitute for having been wrong 100 times already. Tools help, but almost nothing debugs for you. The debugger built into Anaconda exists, and it is not very good. Python Tutor is genuinely good, especially on small programs because it walks you forward one statement at a time and shows the value of every variable as the code runs. Print statements are also good with a caveat. You have to know where to put them, and you have to read them deliberately. If print statements are not yet second nature, Python Tutor will serve you better. Whichever you choose, be systematic. The failure mode is changing a variable here, flipping a condition there, and firing the tester again to see what happens. That is not debugging, that is shaking the box. Some bugs announce themselves. Python raises an error, names the type, and points at the line. Those are the easy ones. An index error means you have run off the end of a sequence. The first move is mechanical. Print the index you used and print the thing you indexed into and compare the two. A type error means you asked for an operation the types do not support. Casting a list to an integer raises 1. Dividing a string by an integer raises 1. Both are usually a one-line fix. A name error means you used a variable you never initialized, usually a typo, or a line you meant to write and did not. A syntax error means Python could not even parse the file. Indentation off by a level or a parenthesis you never closed. 4 types, 4 familiar causes, and in every case, the interpreter has already told you where to look. Logic errors are the hard ones. Nothing is raised, nothing is underlined. The program runs happily to completion and produces an answer that is simply not the answer you wanted, and there is no line to point at, because every line is legal. This is where you deliberately engage a different part of your brain. Think about the problem before you start writing it. Draw a picture of what the data is doing. Take a break, take a walk, and let it surface in the shower or in bed. Talk it through with a friend. Explaining your own code out loud is often enough on its own, which is why programmers explain code to an inanimate object, a rubber duck on the desk, and get their answer anyway. Pull it together. 3 sources for a case: intuition about the problem, plus the 2 discipline techniques, the specification alone, and the code's own paths. Black box cases survive a rewrite. Glass box cases cover every branch and every loop, 0 times, once, and many times. And they still need boundary values because a path complete suite passed a function that mishandled -1. When a case finally fails, work systematically. Step through it in Python Tutor or place your prints on purpose. If Python named the error, read the line. If it did not, the error is in your reasoning, and you go get a duck. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.